What we can do is find this equation of a line that represents this kind of best fit for our data. Then we want to draw a line that is simultaneously as close as it can be to all of the points at once. So with that, what we could do is try to draw a line. And like most of my data is starting below here. And then I would just want to try to make a straight line through the data that would be close to everything. So like I wouldn't want to go too far up here because then I'd lose a lot of information. Here's pretty good. Maybe I'll go with here seems to be pretty close. So what we just want to do is try to capture or just create small distances from the data as much as possible. What we'll be doing is GeoGebra is going to find this line for us. This is called line of best fit. It's also called the least squares regression line. It is also called just the regression line sometimes. There's a few different terms you're going to see, but it's going to be this equation of the line going through the data. Now, when we create this line, what we could look at are the residuals, which is basically a difference in Y values or a difference in outputs. It's a difference in outputs. So what this line provides us with is we could also call this like the prediction line. This line is saying values that we predict, so that if we said Y was 1100, and I said, what could I expect for an airfare? What I could do, since I don't have an actual data value, is I could use the line. I could say, well, we'd be landing about right here, which would equate to a little over $200. So if we know where we're landing on the X value, we could use this equation of the line to make a prediction for us. And then what comes along with that is the strength of our data. The stronger the data is, the better this prediction line is, like the more we can trust it. But then as our data gets weaker, the less we're going to trust this line. So for the residual, the actual calculation goes, you take the observed value, which that's coming from our data. So this is basically taking your Y data value, and you want to subtract it from the predicted value, which is coming from the equation of the line. Now the equation of the line will be given to you in this form right here. It's the same thing as our general equation of the line, y equals mx plus b. It's just for slope, we use b1. B with a little subscript of 1 is slope. And then b sub 0, or b naught, is our y-intercept. But it relates to the same structure that slope multiplies with x, and then intercept is our constant that's adding on the outside. And then for notation, instead of using y equals, we use y hat, and the hat just represents that this is going to be a predicted value. So if we plug in a value for x, this is going to predict what we get for y. So it's going to be this difference for a residual of taking a y coordinate that we actually observe from our data minus what we predict from our line. And this describes a difference. It's a difference in outputs. It's also this difference between what was observed and what's predicted for our data. Now, what we can imagine visually is happening with these residuals. Let's compare these two residuals. So it'd be taking this y value up here for this coordinate at 1200 and 300. And what I'm doing is I'm finding this distance to the line. So what I'm looking at is right here, and we want to find this distance between what was observed minus what was predicted. And what I can see here is what I observed is higher up than my line. So if I'm taking a difference between these two y coordinates, then what I'll have is a positive value coming out. It'll be this positive residual by taking this large observed value minus predicted value. And that's going to happen for any number that's above this number line. So any dot that's above that predicted line, your residual is going to be positive. So when you calculate residuals for those values, it should come out to be positive. And what this relates to in terms of how we're predicting values it's underestimating what's actually happening. Because if we imagine looking at this case of 1,200 where they traveled 1,200 miles, it would be that, say I was buying the ticket, it would be that I was buying a ticket for traveling 1,200 miles, and my prediction was to spend a little over $200. Instead, I had to spend close to $300. So the prediction, what was given to me, was lower than what actually happened. So this is where the line underestimates. Then if we land below, so say I look over here at that value. So I have my output of what was observed, and I'm looking at this distance to the line. So I take my y value from what was observed and then subtract what was predicted. Well, now what I'm taking first is a small value minus a large value. So if we land below this line here, our residual is going to be negative. And what that means, like in this case of traveling over 1,400 miles, say I was using something to predict the cost of my flight, it would say, okay, you're going to have to spend about $275 on this ticket. But then when I actually bought my ticket, it was closer to $225. So it's that what was predicted was higher than what was actually observed. So this is where the line overestimates. Then the only other case for residual is if it's equal to 0. And that would come through like in a case kind of like down here. Even more so, it should be exactly on the line. So if we had a dot exactly on the line there, if we took this difference between what was observed and expected, then they're going to be the same. So when you take that subtraction, you're just going to get a 0 out. And that would be a case that, like, they predict I would spend $300 and then I spend exactly $300. So this is where the line is perfect. It gave me the perfect prediction for what would happen. I'm going to delete that dot since it's not an actual data value. So when we calculate residuals, it can give us an idea of how the line is behaving. Is it overestimating or underestimating? Basically, if it's positive, it's underestimating. If our residual is negative, it's overestimating. And when you calculate these residuals, just make sure you get the order correct. It always goes observed minus predicted. So this equation for the line that we're seeing, it relates to y equals mx plus b. We just use y hat because we're predicting values. b1 is our slope, and that's representing, if it's positive, it's telling us the increase. If it's negative, it's telling us the decrease on average of the y variable for 1 unit increase in the x variable. So when we make sentences describing the slope, what we'll work with is if we increase x by 1 unit, then slope, that b1, is the, or actually, let me change that a little bit. We would say y increases or decreases by our slope units. So use this form to help you make a sentence for describing slope, and we'll do that as an example on this next page. And then Y-intercept is describing what happens when x is 0. So if x is 0, y is whatever our intercept is. And when we make this sentence, sometimes it won't make sense. So when it doesn't make sense, we just say it doesn't apply, really. So especially when this comes out to be a negative number, often that doesn't work in context. So slope you can always interpret. Y-intercept sometimes you can interpret. So let's look through these pieces using that data from the airfare of traveling away from Baltimore. So first, finding the least squares regression line. And out there are these formulas for calculating slope and intercept, but we're just going to use technology. So for finding this, use GeoGebra. And this is where in GeoGebra, it's very important to be rounding to at least 4 decimal places. because if we round this regression line too much, it's going to change everything. So if we go to GeoGebra, we have our data in here. Say we already made our scatter plot. I'm just going to close down our statistics over there. Down at the bottom here, it says regression model. And right now it says regression model none. What you want to do is open up that drop-down menu and change it to linear. So if your rounding rule isn't set to 4 decimal places, these values here will be rounded too far. So make sure you're seeing 4 decimal places when you get out these numbers here. And this is our equation for the line. Now it is showing y, but it is good habit that when you write this down on a piece of paper, use y hat, because technically these are predicted y values. In terms of what y actually is, that's coming from our actual data set. Those are y in the column B. Y hat is coming from this equation of the line. So what we have here is, if we go back to our paper, what we found is y hat is 0.1373 times x plus 81.7636. And then you could also use notation that uses the wording of our problem. Like this is predicting airfare. So you could say predicted airfare, you just need a little hat on top of that word, is 0.1373 times distance plus 81.7636. So this is a common form to use in linear regression, and it's nice because then when you get values, you know what to plug in where. So that's how you get your equation for the line. Now with this, we're going to interpret slope and intercept, and slope will always be what's multiplying with your x value. So that's going to be our slope, the 0.1373. And then intercept is going to be that 81.7636. Now in making our interpretation, so for slope, we want to say if we increase x by 1 unit. So x in this case is distance. So it's going to be if we increase the distance by 1 mile. And it's always increased by 1, because we're talking about what if we move along the x-axis to the right-hand side and just by 1 unit. So if we increase the distance by 1 mile, then what we can say is y increases or decreases by slope units. So if we increase the distance by 1 mile, airfare, our y value, and it's going to be increasing. Because it's positive, airfare will increase by, and then this is in dollars. So it's going to increase by, let's say, about 14 cents. So for each mile that we add on, airfare is increasing by about 14 cents. So that's how you would interpret slope there. Then for the y-intercept, so this is what happens when x is 0, which means if our distance is 0. If distance is 0, this right here is our airfare. So if I went and kind of translated this directly right now, it's that if the distance we travel is 0 miles, the airfare is $81.76. Now that doesn't really make sense. That would be the equivalent of just not traveling and then an airline saying, hey, you didn't travel, now pay me $81.76. Not so much. But what you could think of is in terms of buying a ticket. Say you're traveling. If you don't go anywhere, there's already going to be this charge of $81.76. And then it's going to start increasing based on how far you're traveling. So we could think of as that this is kind of the base charge. The base charge for a ticket is $81.76. So sometimes it might look like it doesn't make sense, but think in the context of things of how it could relate. Estimate the cost of a ticket if they are traveling 200 miles from Baltimore. So what we're saying here is, what if X is 200? And we're estimating, which basically means we want to find a predicted output value. So what this will do is we're looking for airfare, and we want to estimate it based on our equation for the line, but we want to plug in 200 for our distance. Now, you can calculate this by hand. However, like I said, these values are rounded, and even rounding to 4 decimal places should get a lot of accuracy out from that. But to get the most accurate solution, you'd actually want to grab it from GeoGebra. In GeoGebra, at the bottom here, you can see this wording for symbolic evaluation. What this is saying is plug in a value for X, and it's going to plug it into this equation for the line, but it's going to use the most accurate form of this equation for the line. If nothing was rounded, what would be our output? So in terms of showing work, you can show how it would plug in, but for calculation, go ahead and use GeoGebra here because it'll be more accurate than using that rounded form of the equation. So if we plug in 200 here, our output would be 109.22. That would be our airfare. So this is going to be 109.22. And then in terms of a sentence, it's that if we travel 200 miles from Baltimore, the predicted airfare, and you want to use that word predicted because this isn't the actual airfare that's occurring, this is just the airfare we predict to happen based on the equation from the line. So the predicted airfare, or you could use that word estimated or expected, is $109.22. So in plugging in values for X, it's best to use that function in GeoGebra so we can get an exact answer out. Then, which airfare has the largest residual? And to see this, we could look at the scatter plot, and what it would look like is the value that is farthest from the line. So if we go back to GeoGebra for a moment and look at our exact line here, and we kind of just imagine these residuals coming through from each of these dots and mapping these distances from the line, what we could see is this value up here, this is going to create the largest distance from the line. Everything else is fairly close. So what we could do is look at, okay, this is, well, what would probably be easiest is this going to be the value with the highest airfare. So that airfare of $350 and with the distance of 946, that's going to be making this largest value here. So it's that point 350, 946. If we just go back to our data for a second to see where did that value actually come from, that's coming from Miami. Sorry, I realized I just mixed up those values. But Miami is where we have an input of 946, output of 350. So Miami is going to have the largest residual. To find the actual residual itself, what we want to do is take our observed value minus the predicted value. So again, the observed value is going to come from our actual data. So we actually have that coordinate already. So taking that airfare of 350. And then for predicted, what we want to do is see if we travel that distance, if X is 946, what would be our predicted airfare? So with that, what we could do is in GeoGebra, go to that symbolic evaluation and say, what if we were traveling 946 miles? And that's saying our airfare should be about 211.61. So for our predicted value, we want to use this 211.61. So our residual is going to be 138.39. Now, for making a sentence for our residual, what we want to realize is that this is the difference in airfare, and simultaneously in terms of underestimate versus overestimate, this is saying that our line underestimated. If we were getting this predicted value, this is the case where the airline would say, we predict your ticket should be $211, but then when I go and buy it, it's actually $350. So they underestimated what I would have to pay. So for this residual, for the ticket to Miami, the linear model underestimated by $138.39. So that's how we would interpret our residual once we calculated it.